So welcome, ladies and gentlemen, to our session of the Necas seminar on continuum mechanics. This is the first session in the summer semester of this academic year, and we are happy that our first speaker is Dr. Rufat Badal from the University of Erlangen, who is going to speak about nonlinear and linearized models in thermoviscoelasticity. So,
yeah, thanks, Martin. Also thank you for having me here. So I want to report on some recent work together with Martin and also Manuel Friedrich, who also joins us today. So we kind of worked on the so-called model of thermoviscoelasticity. And I don't assume that you know this model, so I will also explain you to that, you this model. You see it here, quite a monster of a system. First and foremost, what I want to mention is that kind of our contribution is twofold. First, most important thing is our work is heavily based on a paper by Milke and Rubicek that came out very recently, and they showed a long time existence of solutions for the system. I'm also very happy that one of the authors joins us today. So we used a lot of their ideas, and in particular, we refined a little bit their result. So this is kind of the first half of my talk, where I explain you the slight refinement that we did. And I cannot do it without explaining you more or less the system. And in the second part, what we did was a linearization for this specific system. Don't worry, you don't need to know what I mean by linearization. I will explain you to that in a moment. Okay, so let's try to understand what this system is about. I will not do too much rigorous physics modeling. I think Milke and Rubicek have a very nice section for that in their paper. I will just try to explain you this stuff intuitively. So we have two unknowns in this system. The first unknown is y, which you can think of as a deformation. This is, I would say, fairly standard. So we have a map from some time domain 0t and a reference configuration omega, reference domain omega into Rd. And you can think of ytx being kind of the location of material point x labeled by x at time t. Okay, so this function maps describes you kind of the evolution of some kind of material. And the second unknown is theta, and that is explaining you the first buzzword here, the thermo word. This is a temperature. So we also keep track of the temperature in the material throughout this evolution. Just one minor point. Naturally, it would be easier to speak of the temperature as a function of the variable y, because theta is actually the temperature at the location ytx in space. But it's nicer to have both unknowns in the same kind of, having the same description for both unknowns. So we take the Lagrangian approach also for theta. This will have an influence in the equation. I will come to that in a moment. Okay, but think of theta tx being the temperature at time t at the location ytx. Importantly, our temperatures are natural temperatures, physical temperatures, so they are non-negative. This is actually a very important restriction, and it creates some difficulties. Okay, so let's try to understand this W here. So the W is a potential of the free energy, sort of the whole elastic energy of your material. And what's maybe new to you is this is also temperature dependent. So it gets the strain, the gradient of y, which it describes you the local deformation of your material. We will actually show that this gradient of y will always be an invertible matrix as long as you start with one. We have a million of conditions. Milke and Rubicek have also a lot of conditions on this. So this is a very general, more or less general potential. But for this talk, I want not to tell you all of the conditions. And I will also specify on one very nice example that works for those conditions. But keep in mind that what we do is a bit more general than what I show you today. So one such competitor for this W that I have in mind comes from shape memory alloys. This is an example directly from Milke and Rubicek. So in shape memory alloys, you have basically two potentials that only depend on the deformation, not the temperature, the so-called martensite potential and the austenite potential. And one is preferred at low temperatures and the other is preferred at high temperatures. And you have some kind of interpolation in between depending on temperature, which is this A theta. The last term, which is also very, very important, you can think of this as a sort of entropy. Again, the modeling I refer to Mielke and Rubicek, the more precise modeling of this. Okay, for those potentials, we assume very natural conditions, physically natural conditions. So frame indifference for the martensite and eosinite potential, which means if you rotate things by an orientation preserving rotation, then nothing changes. And this is, I mean, for those that are unfamiliar with this stuff, this just means that if you look at your experiment from a different angle, the evolution should be the same up to a rotation. So that's what it basically encodes. It's a very simple, physically simple condition, but it makes a lot of mathematical difficulties. I mean, the paper by Mielke and Rubicek is fairly new, and this provides, to my knowledge, the first existence of the system under those physically rigorous conditions. And also, one of the important conditions is a lower bound on the martensite. It should, so this is the Frobenius norm of the matrix. So this should scale quadratically at infinity. And also we penalize the determinant to become 0. Okay, and we do it by this 1 over the determinant to some power q. Actually, there is a precise bound on this q. This q needs to be large enough to have an effect, which is that the determinant will stay strictly positive throughout the evolution. So this is a very nice argument found in Mielke and Rubicek. If q is large enough, this will enforce your gradient to have strictly positive determinant at every point, uniform in time and space. Okay, and this A, as I told you, it's a sort of interpolation between the martensite and the austenite. So it's a function that is 0 at temperature 0 and goes asymptotically to 1. All right. So in particular, at 0 temperature, only the martensite dominates because this A theta is 0 and this term also becomes 0. And the large temperatures, the austenite dominates because this combination becomes the austenite. Importantly, what we get, by the way, yeah, generally, we don't speak of the martensite. We generally have conditions that tell us and also Mielke and Rubicek have this, that our potential is a sum of a purely elastic guy, so this WEL, and the potential that depends on the temperature. And in particular, what we see here is that the coupling vanishes at 0. It's a very important point. And this is also the potential that appears in the second equation, this W couple. Okay, so now I explain you the visco part of this thermoviscoelasticity. So we have a potential of dissipative forces here. It's a standard thing if you want to model some viscous motion, some friction. This is taking in a strain, the time derivative of the strain, and the temperature. Again, it needs to satisfy nice symmetry conditions, but we have a little bit stricter condition. We assume that it's a sort of a quadratic map, but in the symmetrized quantities, which are the C here, which is the symmetrized version of F, and the C dot, which can be seen as a symmetrized version of F dot. So with regard to those variables, we can write it as a quadratic form. Okay, but because we have matrices, we don't have a matrix here, we have a 4 for the tensor, but the definition is similar to vectors. I use Einstein summation. So this one will kind of slow down the flow. You will not instantly jump to the minimum, to a stationary point. You will take some time for that. Okay, and the last thing is this H here, and you can think of this as a regularizer. So this depends on the second gradient of Y, and I mean, some people call this a second grade non-simple material, but in my opinion, this is just a very nice regularization for your evolution. And this dates back this is quite an old idea. This dates back to Tupin. Okay, this guy is, we assume very nice things of it. It's a convex function enjoying very nice bounds. And you see, it's sort of a regularizer because we want Mori to work. So our P must be larger than the space dimension. Okay, so I think I explained to you kind of the mechanical part. Okay, up to the F you can think of as a force acting inside the material. So let's try to understand the second equation. So the second equation is more or less the heat equation. Okay, but a very physical, rigorous modeled heat equation. So here you have the standard time derivative of your temperature on the right-hand side. It is multiplied, maybe we didn't see this term, by this term CV, which is actually the heat capacity at constant volume. And it has a formula with regard to the coupling potential. Again, I refer to Mielke and Rubicek for the derivation of this. And in our case of this martensite austenite, so shape memory alloys, this will become this quantity. The C here is the constant in front of the entropy. Now, under nice conditions, you can make this term uniformly bounded, independent of F and theta. So if you choose the constant in front of the entropy large enough, you can assure that the resulting quantity is in some positive interval. And it's one general important condition in both papers. Yeah, what is the physical intuition? Well, different materials heat up differently. So if you provide some energy to the material, it will not heat up by the same amount. For example, water has a very large heat capacity, and this allows you for a point-dependent heat capacity in your material. Okay, on the left-hand side, well, we have the heat transport. So this is governed by this K. So this K here is just the heat conductivity of your material. It can be point-dependent and also dependent on the temperature. This point dependence, I didn't write it here, but actually it's possible that this guy is point dependent. I just used a shorter notation. And importantly, this is the point that I made you. We take the temperature in the Lagrangian way. We consider it Lagrangian, but actually the heat transport is happening in the deformed configuration. So it's really important to know in the deformed configuration how close points are together, not in the reference configuration. For example, points can be very close in the reference configuration, but actually extremely close because kind of the material is bended in such a way in the deformed configuration. And the heat equation only sees the deformed domain. So to make things work, you need to change coordinates, and please believe me that this is the right change of coordinates that you see here. Okay. In particular, this is completely well defined as long as our flow never lets the determinant become zero, which is a crucial point. Okay, and then the last two terms, you can think of them as a heat source or heat sink, but because we have a coupled system, this is not a priori known. This depends on the Y. So the first term, the Xi here, it's always a heat source. So its general formula is given by the viscous potential like that. But because we assume that our R is quadratic in F dot, this actually, I mean, if you differentiate a square, you get back the potential up to a factor. So this exactly is of this form. And the way to think about this is if material deforms very drastically in a short amount of time, it creates a lot of heat. Okay, so if your grad Y changes heavily, so the grad Y dot is large, this will be a large positive number. So this will create heat locally in the material. And the last term, well, it doesn't have a sign, but you can think of it as a heat source or sink. And this comes from this shape memory effect. So what it can do is it can take heat and create elastic energy from that. So then it's a negative term, or it vice versa, it can use up a bit of elastic energy to create heat. Okay, but importantly, this doesn't have a sign. Okay, now we also, and Mielke and Rubicek also do that, we kind of consider a very general setting. So let's think about the boundary conditions for a little while. We assume that our boundary is split into two parts. On one part, we prescribe forces, and on the other part, we prescribe Dirichlet conditions. I don't want to talk too precisely about that, but so this is the surface divergence, and nu is the outer unit normal. But importantly, it just allows us to model a certain force acting on the boundary of the material. And our Dirichlet condition will always be fixing the Y to the reference domain. Okay, so YTX is equal to X. So then we have a third condition, which is with regard to the this H, the second order term. It's more or less there so that a certain integration by parts doesn't create boundary terms. I will come to that in a moment. So let's not think too deeply about that. But importantly, the fourth condition tells you we allow for some heat transfer at the boundary. So kappa is a heat transfer coefficient. It's non-negative. And theta flat is the temperature outside your material. So if kappa is positive, it allows for a transfer of heat at the boundary. And we have initial conditions. We start with some initial deformation, and we start, of course, satisfying the Dirichlet condition. and having positive determinant everywhere. And we start with some initial non-negative temperature. Okay, so this is now the monster system at the end that you get. Now for the talk, I will simplify. So in the paper, you can find the most general setting, but I think in the talk, it's a bit too complicated to keep track of all the objects. So we will consider 0 internal forces. We will forget boundary forces. We will fix the boundary. The initial condition will be prescribed at the complete boundary. And also we will don't allow heat transfer at the boundary. This just simplifies. We don't need to keep track of this exterior temperature. So for this talk, we will talk about this system, but actually in the paper, you find the most general setting. Okay, now I wanted to talk about a little bit on the weak formulation for which Mielke and Rubicek and also we show existence of. And for that, we need kind of to change a little bit the thermal evolution. There is a very nice trick, again, due to Mielke and Rubicek, that rewrites this equation in a, I would say, nicer form. So what I don't like about this equation is this nonlinear guy in front of the time derivative of the temperature. And there is a very nice trick to get rid of that. Actually, it's physically motivated, but let's keep this computational for today. And the idea is to look at the so-called internal energy. This is, again, a map of T and X, and it's given to us by this formula that you see here. Again, there is a physical intuition for that, but forget the intuition for the moment. So now what you do is you can try to think about the time derivative of this internal energy. So instead of the time derivative of the temperature, we look at the time derivative of this W. Then you apply the chain rule, and what you get is this term here. And what you see here is that those two terms, they are appearing in the equation. So actually, if you remember, the heat capacity was defined in exactly this way. So if we combine this, we end up with this equation, which is equivalent. Okay, so the definition of W plus this equation is equivalent to the first here. And the nice thing now is that this becomes kind of linear. So there is only a time derivative. There is nothing in front of the time derivative. Of course, there is a non-linear relation between W and theta, but actually for the analysis, it's not that big of a problem. And we replaced this term by, in my opinion, not even more complicated term here. In fact, it's even a bit simpler because you have less derivatives. So we will really look at this formulation of the heat equation and not that one. Okay, so let's come to the weak formulation. I think the mechanical weak formulation is fairly straightforward. You test with your Z. You need, of course, it completely supported so that you don't change the boundary conditions. And then integrate by parts. Okay, and you end up with this condition. By the way, here you need this magical boundary condition for the H term, because for this one, you need to do twice an integration by parts twice. You know, there were two divergences. Okay, but no matter what, please believe me, that is a very natural weak formulation. For the temperature equation, you could do the same. You could test with a phi and integrate by parts, and then you would end up with this condition. But this is not exactly what we will show. And maybe the main point that you can take from this talk is that actually the most problematic thing about this work is the heat equation. You might not believe it, but the heat equation creates the biggest trouble. In fact, this is not a very, very nice heat equation. It's a so-called L1 heat equation. I will come to that a bit later on. And the bad thing about this heat equation is that it doesn't provide us very good regularity in time. So actually, we will not have good compactness of time derivatives. In particular, we will not be able to pass to the limit to derive a weak formulation where there is a time derivative of W appearing. So what usually people do is they show a bit weaker notion of solution by putting the time derivative to the test function. So if we integrate by parts, we can push this guy to the test function. Okay, so we will get this term plus boundary terms. Now, I told you the time regularity is very weak of this solution. So we will not be even able to evaluate the W at time t and time 0. And the way to overcome this is first you take test functions that are vanishing at the time horizon. Okay, then this term vanishes. We don't even need to think about this. And this is good enough because those phi's are still general enough to give you the interior equations. And for the W here, well, instead of evaluating at 0, we simply plug in the initial conditions. Okay, and this is the notion of solution that we will try to find. And by the way, Mielke and Rubicek, this is their fundamental result. They show a long time existence of such solutions. Okay, now let's come to the differences that lie in the scheme to get those solutions. So I will now tell you the variational scheme behind the existence result. And the start is, I think, very straightforward when you deal with two equations that are coupled. So the scheme will be staggered. Staggered means that I will first evolve the material while keeping the temperature fixed. So there will be a so-called mechanical step, only deforming the material. And then I will transport the heat inside the material while fixing its shape, its current shape. And then I will alternate between a mechanical and a temperature step. Okay, so let's suppose that we initialize our scheme at y0 and θ0. We have some discrete step size, time step size. And just for simplicity, I assume that my time step size divides the interval so that things look nicely, okay? Of course, this also works for general taus. Okay, and let's suppose that we have already constructed all the steps up to k-1. So I will tell you now the next kth mechanical step, and I will tell you the next kth thermal step. Okay, let's think about the mechanical step. I just give you the intuition how one can come up with it. There will be no theory here. So what you do is you look at the weak formulation that we had before at a fixed time t. So the fixed time t we can test with a z here, and we have this condition. And what we do now is we time discretize this equation. So the time derivative that you see here becomes a discrete time difference. And we need a clever choice. So anytime you have a grad y here, we need a clever choice if you take here a grad y of the k step or grad y of the k-1 step. So this is actually the point where you need to work a lot to find a combination that works nicely. I tell you, this is the good combination. And then, okay, and then one minor, sorry. And then one minor thing just to recover kind of the minimizing movement definition of this flow for those people familiar with that. You can pull out this tau here because the R is again quadratic in the second component and its derivative is linear, so that you can just pull out this tau. Okay, and third step is you take this and find an energy whose Euler-Lagrange equation is given by this. And it's super simple to do because everywhere you have derivatives, so it's quite easy to integrate. And you end up with this variational formulation. So the kth deformation is given to us by this minimization process. And this is, I would say, a very classical minimizing movements perspective. So you can think of this as being the energy, and you can think of this as being the dissipation. Okay, and you have the penalty with the tau. So for those of you that ever saw minimizing movements, this is, I think, very standard. Now, this is the difference to Milk and Rubicek. Let's look at what they are. Okay, and last thing is, I will just write shortly W2P functions, which are equal to X at the boundary simply as W2P ID. If you see this term anywhere in the slides. Now, Milk and Rubicek, they consider a similar variation formulation, but they need to regularize it. So what they do, they fix a very small epsilon, and they add this sort of L2 penalization term to the energy to the variational formulation. Now, if you let tau go to 0 and you hope for the best, what you will get is a solution of a regularized version of your mechanical evolution. So additionally, you will get this term here. And then they have another argument where they show that for each epsilon first, they have a solution, and they let epsilon go to 0 to get then rid of this regularization and actually recover a solution of the real system. And our only advantage is that we don't need to do that. So we got rid of this regularization. Our time discretion directly recovers a solution. Okay, let's go fast to the temperature step. So now we deformed our material. We have available YL for each L from 0 to K, and we have temperatures available from 0 to K-1. And now I will tell you how to make the temperature step. Here you start with the strong, slightly stronger formulation of your heat equation. I don't integrate by parts. It's quite important. But the idea is the same. You time this, sorry for the big equations, just a big system. But the core ideas are very simple in this case. So you time discretize your derivative of the internal energy. Remember, this was the definition of internal energy. And again, you need a clever choice of when you use K and when you use K-1. I want to highlight that this guy is very, very delicate. So each index here is very carefully chosen. In fact, if you change one of the indices, our proof doesn't work. Actually, if you change any of the indices anywhere here, we have no idea how to do the proof. So this is the only selection for k and k-1 which works. Okay, and then lastly, you do, now again, you integrate, you find the energy functional that gives you this as a weak formulation. And it's actually very straightforward because you have the new temperature only at 2 occasions. For the first one, you just take the antiderivative. This is nothing else here. I take the antiderivative of the internal energy. If I take the derivative, I will get this term. And here we have a linear term, so its antiderivative will be a quadratic term. And all the other terms, they look crazy, but they don't depend on the new temperature. So you can think of them as being a constant. So their antiderivative is simply all of the terms combined times theta. Okay, this is again a little difference to Mielke and Rubicek. Okay, sorry, there is a little miracle. This is a very crucial point. I think the most non-trivial point in the paper. The problem about this weak formulation, the problem about this weak formulation is it's designed so that if you minimize over all temperatures, also temperatures that are possibly negative, then you will get the correct equation. But you remember, we had a condition that the temperatures must be non-negative. So you could require this here as a constraint, but then it's non-trivial that the Euler-Lagrange equation holds, because this one only works if you can take variations in any direction. But the non-negativity constraint might influence that. Okay, and the miracle is that we can show that actually this minimization will give us always non-negative minimas. One minor technical point, to be able to write this problem for all temperatures that are also negative, we need to extend the internal energy to negative temperatures. But that's fairly simple because the internal energy is, you can compute at zero temperature. So we extend it simply by 0 to negative temperatures. But the very non-trivial point in this paper is that we can show that magically the minimum will be non-negative. Okay, and what are the difference to Mielke and Rubicek? So this is, by the way, still our energy formulation. I just wrote out this H term. And Mielke and Rubicek need to regularize at 2 points, and need to regularize at 1 point, and they need to do an implicit step instead of an explicit step at another point. You can see it here. So this was, if you remember this dissipation rate, what they need to do is they need to truncate it, sort of. So instead of xi, they look at xi plus 1 epsilon xi. And now if xi goes to infinity, this term is always bounded. So what this regularization does is it smoothly truncates the dissipation rate. And another difference that they have is, for us, we had here an explicit step. We plugged in here the old temperature. And Mielke and Rubicek, they need to have here an implicit step. So this will result in an Euler-Lagrange equation, which has the new temperature here. And only for this situation, they could prove the non-negativity of the temperature. So I think the main contribution of us, it's the only contribution with this regard, is really showing that you can do that without this implicit step. And then a lot of things really magically work out that didn't work out in the time discrete setting for Mielke and Rubicek. Okay, and then just briefly, I will come to more precise statements at the end. We have now the result that, so we have the result that, okay, if we interpolate in a piecewise constant way all of the steps, then those interpolation converge in very different topologies to a weak solution of the nonlinear system. Weak solution in the sense that I told you before. Don't worry, in case you're interested about all the convergences, I will tell you that later on. Okay, so really the only contribution of us is showing how to do things without regularization, but we show the same existence result as Mielke and Rubicek. Now a short break, I show some animations and then we go to the second part of the talk. So I did some computations, simple computations for this minimizing movement scheme. So we will look at examples in 2D. Our initial material will be just a square, and we will fix the left side of the square. So this is our partial Dirichlet condition. And inside the square, I will assume some constant temperature, sometimes 0, sometimes positive. And the exterior temperature will be always fixed to 0. As potentials, I look at this guy here. And as a dissipation, I look at this here. You see, I was a bit lazy. Those potentials, they're not invariant under rotations. I mean, this is just laziness. You can think of also of nice potentials that are rotation invariant. But I think qualitatively, this should not change too much. Also, one thing that I didn't do, again, because of laziness, I didn't implement the second grade, the second order term. Okay, so let's start with an example where we start with 0 temperature and our material is thermally insulated at the boundary. Okay, so you see it starts to expand and heats up in this way. So you see the effect of the dissipation rate. The material expands and this expansion creates heat. But because this expansion is very uniform, it creates uniform heat everywhere. So the heat equation doesn't need to work to diffuse the heat. Why does it even expand? Well, if you look at the definition, at low temperatures, this term is, okay, maybe, yeah. So, but basically at low temperatures, my material prefers to be twice as wide as it's high. And at high temperatures, it prefers to be a square. Okay, that's why the material expands, because initially it's cold, so it likes to be twice as long as it's high. So it will expand to the right. And notice here also that the stationary point is not exactly a 2x1 triangle, because in this expansion, it created heat. And because there is heat in the material, it will not prefer the perfect 2x1 triangle. It will prefer something in between the square and the rectangle. Now the same example, but now I allow the heat to disappear at the boundary. So you will see the expansion creates heat, but there is heat dissipated at the boundary. So it cools down, and this one will have as a stationary point, the 2x1 rectangle. Okay, and the third example, I start initially with some heat, and I also lose heat at the boundary. So it will now not instantly go to the 2x1 rectangle. It will wait a little bit until it cools down, and then it will start to expand. And this is usually the experiment that you see with shape memory alloys. You heat them up, you deform them, and then while they cool down, they get their old shape, which you see here. Also nice is that the corners go faster to the 2x1 rectangle because they cool down faster. So it kind of gets the kind of a bend there. Okay, but this will give you the stationary point from before. Now I wanted to show you just 2 examples of forces. So internal forces, you can think of gravity, as you see here. So it's kind of bent down by gravity. So it's sort of like a hanging wire, but it's hanged only on one side. And lastly, just to get everything together, so I have a heated square. I can lose heat at the boundary. And imagine I press with my finger on the right-hand side here. So what you will see initially is that the material doesn't want to expand. So it will give in. And then at some point, it will start to expand. It's nice also, it gives in. And then when it's cooled down fast enough, it starts to expand. And it reaches a non-trivial, I would say, stationary point. Okay, good. So just some animations. At least numerically, you might be convinced that the result should work. Okay, good. So now we jump to the second part, the linearization result. This is unique to our paper. So for this, we need some more special conditions on the potential. So we consider now an elastic potential. Think of this Martensite from before that has only one well. And for simplicity's sake, we put this well at the rotations, but actually you can put it anywhere. Like you can look also at SOD times an invertible matrix. This is just for simplicity. But it's important that it's a single well. And yeah, this is kind of encoded by this. So we say that our elastic potential now is 0 at the rotations. And it at least it has a lower bound that scales like the distance squared to the rotations. Okay, and for the second order term, we need that it's 0. At 0, which was not required before, but now we need. And importantly, this induces that the map, which is identity, so material that doesn't deform, stays the reference configuration, and 0 temperature is a stationary point of your system. And the reason why we like this is because we will do linearization at this point, and you should only do linearization at a stationary point. So what is linearization? Well, what we do is we assume that we are extremely close to the stationary point. So we assume that our initial deformation is the identity map plus a little perturbation, okay, initially. And also we assume that our temperature is very close to zero temperature. So this parameter epsilon will measure you how close we are to the identity. And epsilon to the alpha will measure you how close we are to zero temperature. You see here, we have another degree of freedom here, how the temperature scales with regard to the deformation. And actually you will see a different linearization depending on the alpha. Okay, so we assume here some positive alpha. And now our previous result told you that if you start with this, you get a solution of your system. And now comes the interesting question. So if you take this solution y epsilon and theta epsilon that is guaranteed by you by this long-time existence result, you can look at those rescaled quantities u epsilon and mu epsilon, and they're naturally rescaled. Well, initially y epsilon was very epsilon close to the identity. So it makes sense to look at the quantity y epsilon minus identity over epsilon along the flow. And this will be kind of your rescaled deformation. And to look at this rescaled temperature. And now the question is, can we find another system, let's call it L, so that its solution, u and mu, approximately, and I will make this precise in a moment, approximately describes you the evolution of the rescaled quantities. And you might think, okay, if you start close to a stationary point, things should not be too wild. So maybe the system is much, much simpler than the original system. And actually it will be. The L stands for linear, and a lot of terms the system will be magically linearized. So from the application point of view, it's very nice to have this result. So if your initial configuration is like I told you here, then it makes sense to maybe solve the system L and get a very good approximation for y epsilon and theta epsilon. Okay, so I thought that instead of giving you a deep theoretical insight, I just formally derive you the system that we get, and then you can be guaranteed that we prove this rigorously. So let's do some formal argument how can we guess the system. Actually, we only do it for the mechanical equation, else it gets too boring. So yeah, just to repeat, suppose that we have the solution, y epsilon theta epsilon. I use the same definition for mu epsilon and mu epsilon from before. And now what we do is simply tailor, but the magical thing, the formal thing is that we assume that this quantity u epsilon and mu epsilon and all necessary derivatives are L infinity bounded. This is a highly non-trivial result. I mean, this tells you that you need to have a priori bounds on your solution that are scale invariant and are in L infinity, which by the way, we never have. So usually we'll get some LP bounds, but for the moment, let's assume that we have L infinity bounds. And then we simply tailor all the terms in the PDE. So for example, this is a term that appears in the mechanical equation. And if we tailor it at the identity map, so here the identity matrix and zero temperature. So let's tailor first the elastic, potential. We get this here. So this guy is zero because our elastic potential is minimized at rotations and identity is a rotation. So this vanishes. And for this one, we abstractly generally define it as a matrix. This is a fixed tensor, CW. And note here that the CW by our symmetry condition actually becomes a symmetric matrix. So instead of taking the scalar product with the gradient of u epsilon, we can also take a scalar product with a symmetrized quantity, just for the experts that are familiar with this. So we get this here. If we tailor the coupling term, we get, this guy here, we get those three terms. Again, there is a lot of simplification happening. If you remember, oops, I lost my mouse, here. If you remember, our coupling potential was vanishing at zero temperature. So if you take the first partial derivative, it will still vanish. And the same holds true for this guy. So both of those vanish. And then we remain with this mixed derivative, del f theta, at the identity matrix and zero. This is, again, a symmetric matrix, which we call B, okay, times the temperature. And the error term is 2 times minimum of 1 in alpha. So there is a dependence on the alpha scaling. Okay, so we end up formally with this expansion. And now what you see here is a constraint on the alpha. So we want to divide this equation by epsilon because we want to see something that depends on the u. So at the end, we want some equation for the u. So this tells us that we need to divide by epsilon. But this forces the epsilon to the alpha term to not explode. And this can only happen if alpha is larger or equal than 1. So you see here is that alpha cannot be smaller than 1 if you want to have some nice limit containing u, the limit of u epsilon. Okay, similarly, you can do the stuff with the second order term. Actually, there it's much simpler. I use a condition on this that the derivative scales like p minus 1. So if you plug in the scaling for u epsilon, you get the term that is scaling like epsilon to the power of p minus 1. Now, if you remember, p is larger than the dimension. So this is larger than 1. So this is and the dimension is larger than 2. So this is a negligible term with regard to epsilon. So this tells you formally that the regularization vanishes when you do linearization, which we can, by the way, show rigorously. And lastly, I will not do that, but you can do it. You can similarly do a Taylor for the viscous term. And what you get is a fourth order tensor, the CD here, times the symmetrized, times the matrix, times the symmetrized time derivative of the gradient. Fourth order tensor time matrix gives you a matrix again. Okay, so we end up formally with this sort of limit. Okay, now again, we assume that all the quantities, all the rescaled quantities converge in L infinity and all that there is. This is the formal part of this argument. But formally, you get this system. And interestingly, you have here this is a Dirac delta, this term is 0 if alpha is not 1, and else it is 1. So you basically see this effect of the B only when the temperature scales like epsilon. Else you don't see this effect. It's a very nice insight. Okay, I will spare you from doing the thermal equation with me. Please believe me that this can be done. And in the thermal equation, we will also see that alpha cannot be larger than 2. Else again, there is some term that explodes. And only if alpha is equal to 2, you will see this term in the linearized limit, which you can think of as a linearized version of the dissipation rate. So the dissipation rate only appears if your temperature scales like epsilon squared. But this equation greatly simplifies. I mean, it's a standard heat equation. Here you have just a constant. It's the heat capacity at the identity matrix and at 0 temperature. So this is just a constant. What I want to remark here is something very nice happening here. And not only the system becomes simpler, each equation becomes simpler because it becomes linear. No, but also the system decouples in some sense. So if you take an alpha that is strictly between 1 and 2, there is no coupling between the mechanical and the thermal side of things. So basically, the thermal equation just distributes the initial rescaled heat, and the mechanical equation just deforms the initial deformation. And there is no coupling. And only at this critical regimes where alpha is 1 or 2, you get a partial coupling. So either the mechanical equation sees the temperature through this B matrix, but in that case, the thermal equation doesn't see the mechanical equation, or vice versa, the mechanical equation sees the deformation through this linearized dissipation rate term, but the mechanical equation doesn't see the temperature at all. So that's also a very nice thing that we saw. Okay, now we come to the rigorous part where I just tell you the result and all the convergences, and then we're done. And note here is that we needed to regularize here. So we didn't need to regularize for tau, letting tau go to 0, but our linearization procedure needs regularization. The regularization is quite straightforward. What we do is we change the psi in the heat equation by a regularized version of psi that is depending on alpha. And the regularization that we do is very simple. The psi reg is simply psi as long as the psi is smaller than 1. And else it is a root of psi for large psi's. And the important thing about this regularization, if you look at our proof, what we need is a better integrability for the psi. And this is the point that I want to say. This is an L1 heat equation. This is the takeaway from today for today is this is the bad guy in the system. For the psi, we can only show that it's L1 in time and space. There's just naturally no better estimate for this. And that's why it's an L1 heat equation, because the heat source is L1. And for our linearization to work, the heat source needs to be a little bit better integrable. And this depends on alpha. It needs to be L2 over alpha integrable. Okay? And in particular, this regularization assures that if you know that psi is L1, then this regularized guy will be automatically L2 over alpha. Also notice here is that we do not need any regularization for alpha equals 2. So there, the word is nice. I don't know why, but that's the case. So actually for psi, for alpha equals 2, we don't need any regularization at all. Okay, but notice here, this is a good regularization. It doesn't change the limit of your, this is one of our crucial results. This regularization doesn't influence the linearization limit. We get the same limit, but we do it rigorously. Okay, now let me come to the final result where you can see a little bit the convergences that we have. So this is the diagram that we should have in mind. On the left-hand side, you have kind of the time discrete setting. On the right-hand side, you have the time continuous situation. On the upper part, you have the nonlinear case. And on the lower part, you have the linear case. Okay, and we have a sort of commutativity in this diagram that I will explain you slowly. So the first result concerns, again, vanishing time discretization. So just to repeat, we have the staggered scheme that you have in mind, and we can do it with regularized and with not regularized psi. This is the important point. So for tau to 0, we do not need any regularization. And what we prove is that as tau goes to 0, those proper interpolations of those steps, they converge to the time continuous nonlinear solution of the system. And the convergence that you should have in mind is, I mean, I just tell you a bit about the precise convergences. So in particular, we have L infinity convergence in time and W1 infinity in space that I will shortly write like that for the deformation. And for the temperature, we have, this is a bit mysterious maybe to you if you never saw this. So we have LR convergence in time and W1R convergence in space. But surprisingly, the R cannot be 2. So if you think about the normal heat equation, this should be a 2 here. But the problem is this is an L1 heat equation. This has some influence. In fact, it will kind of make the result a bit worse. You get a kind of integrability up to d+2 over d+1. And believe me, this is optimal. And if you don't care about the differentiability of the theta, you only care about theta itself, you can improve the convergence by interpolation. And actually, you can get LS convergence for S between 1 and d+2 over d. So this is a little bit better than this, but yeah, it's generally still not 2. Okay. Again, I want to highlight here, this is a result both for the linearization and for the large strain case. And for the large strain case, we don't need to regularize. Okay, now we understand this diagonal and the lower arrow. So here you should have in mind, we get rid of the epsilon. So we linearize here. And let me formulate this in the time discrete setting, nonlinear time discrete setting. So here, interestingly, without selecting a subsequence. So before we needed to select a subsequence, but here we don't need. And the reason you will see this solution of the linear system that you had before is actually unique. You can show that. So this will always tell you that you don't need to select subsequences. So without selecting subsequences, we converge every time in H1. So this is our result. So the rescaled quantities, or the U epsilon tau, basically, this converges strongly in H1. The strong part is the non-trivial one. And the temperature, the rescaled temperature is important, converges in the same way as the non-rescaled one from before. So we have LR W1R convergence. And if you don't care about differentiability, we have LS convergence. I think the crucial contribution of us here is that we can basically do the analysis, which takes back to Boccado and Galois. There is a trick on how to get these convergences. We can do it in a rescaled fashion. And Milk and Rubicek didn't do it rescaled because they didn't need it. And they only looked at large strains. Okay, and now we look at this arrow here. So we go from the time discrete nonlinear setting to the time discrete linear setting. And then we have, again, very similar convergence to what you did before. We have strong H1 convergence for the deformations, and we have W1R weak convergence for the temperatures, rescaled temperatures. And now I'm a bit imprecise here. So the mu tau k and the u tau k, they enjoy a similar staggered scheme, but in the linearized setting. And the scheme is much simpler than the nonlinear one. Okay. And lastly, we have also kind of a result for the vanishing time discretization for the linear case. Yeah, with nice convergences. Okay, yeah, so this just should give you a feeling on what kind of kind of scale invariant estimates that we have. You saw that we never had L infinity ones, but this is not needed for the linearization. Those LP estimates that I showed you are sufficient, at least if you regularize good enough. Okay, yeah, and yeah, thank you for your attention.